All right, and hello, and welcome to the EEE 174 CP 185 Lab 1 Part 2. So what I'm going to do is I'm going to cover some helpful hints in how to get started in this lab, as well as going over some of the key concepts to kind of get you through and explain some of the stuff as we go through it. So first thing we'll go over is going to be the steps that we're going to do in Lab 1 Part 2. So we can see here we have the first, it says 5 steps. There's actually technically 6 steps, because we're going to actually, there's one thing that is mentioned here in the very top, which is we're going to take the original program as discussed in Part 1, which is right here, and we're actually going to convert that to an 8-bit program. So what that means is an 8-bit program versus this one, which is actually a 16-bit program. So here we're actually handling our data as 16 bits or 2 bytes, as well as we're using what's called these 16-bit registers. So you have AX, BX, and DX are the registers used in our original program. So we're going to convert this and actually use 8-bit registers. Well, what that means is actually in in debug, or when we're doing our assembly, our registers, we actually have 4 key general purpose registers that we're using, right? So you have AX, BX, CX, and DX. So from here, each of these 16-bit registers are actually comprised of 2 8-bit registers. So for instance, AX actually has AH and AL, BX is BH and BL, and same thing for CX and DX. So what we're going to do for the program is we're actually going to convert our program from using those 16-bit registers to utilizing now the 8-bit registers. So that's a fairly straightforward process. If you guys remember going through the how to do hand assembly video, there was a W bit that we set by changing, I think originally the bit was set to 1. If you change it to 0, it'll actually convert to using the 8-bit registers, and you just have to look at the 8-bit register codes on the table to then do that for the hand assembly. So overall, it's not overly difficult. You just got to change that 1 bit in how to do the hand assembly. So once you do that, that's, like I say, step 0. What we have to do now is we have to change some of the logic in our program. So step 1 here is asking that we use only 1 JG instruction or 1 conditional jump. So the easiest thing for this is actually going back to our flowchart. So we look here in the lab document that we have the basic outline of the flowchart here that we covered in Part 1. And as we go through it, each of these diamond shapes are those conditional jumps, right? So how we change this is we can get rid of one of these conditional jumps, and then from there, we can change how we're going, where we're going to do the unconditional jump to. So there's many ways to do this. There's no wrong answer, but maybe a good idea is one of the ways I'm going to discuss is maybe just get rid of this lower one. And what we can do, instead of jumping back to the add instruction, we can actually jump back to this JGE. So what will happen logically if we walk through the flow of our program is it goes through the previous steps as it did. It checks if the balance, or checks if the value in the A register or AX register is less than 0. If it is, or if it's negative, it goes through and adds. It'll go down to the jump, and after adds, say if the result is turns positive, right, it'll go down to the jump, it'll come back up and check again here at the JG. And if, because the result maybe is positive, it'll flow back down and end the program. The other case could be is if we're going down and we do have a negative result, right, and it adds, and say the result is still negative, it'll go back to the jump. And if we jump back to this JGE, it'll then go back down through and add again. And then once it's completed, it'll leave the loop. Okay, so that's one way we can do for step 1 is getting rid of one of those JGE or having only 1 conditional jump. So getting rid of the bottom one and changing this jump to actually go to the point towards this instruction or this JGE, right? Now, there's more than one way to do this. There's perfectly fine. I'm just giving you one solution or one way to figure out how to go about it, okay? 1 second, and go back to Lab 1 Part 2 here. Oops, passed myself. All right, so that's step 1 right there. Now, steps 2 and 3. So we're going to discuss this. So this is actually what we're going to do is we're going to make new use of no register that were assigned, as well as we're going to use a consecutive memory location for our data from now on. All right. So how we figure out steps 2 and 3 about what register we're not assigned, as well as a consecutive memory address, is actually in a table in our Lab 1 documents. And you'll find it is right here, the hand assembly lab register memory location, right? And you see it pop up. So if you notice, open this up a little bit more. For this document, we have a couple of different rows and some nested rows within a larger set. So below there's an example, and one of the key things you're going to use is actually the first letter of your last name and the first letter of your first name. So first we're going to use the first letter of our last name, and you can see here I have an example with a student named John Smith. So the first letter of the last name is S. And for this case, we're going to look at this row right here. And this row will tell us what register they're not allowed to use. So in this case, if they're S, they're not allowed to use the D register. So again, we had to change to the 8-bit register, so they had DH and DL as an option. Well, for this student, they would not be able to use it. But one of the advantages is we have not used one of those general, or one of those registers we discussed inside our program yet, right? Which is CX. So I can simply replace maybe DX to CL instead of doing DL, right? So it's an easy enough change to make. So that'll give me the register not used. Now, from here, we'll have to find is what our consecutive memory address is going to go put our data. So in this case, again, we're going to use the first letter of the first name. So we use this table and we see we're in this row, and within this row now we're going to look for the first letter of the first name within these options. And we can see here that the first letter of the first name is John, right? So from here the consecutive memory address will be 454. And so we're now going to modify our program. So in the past where we had memory address 200 to store the data, we're now going to put all data after 454 and on. There is one thing we want to note is that when we get to one of these later steps in part 2 where we have to display data onto the screen, you have to use the DX register. And that is the one exception to the rule. So if my register not used is D, you are allowed to use it for a very small snippet of code. And I'll go into that a little bit when we get to that part, which I believe is step 4. All right. So for, again, this example for a student named John Smith, their first letter, they're not allowed to use the D register, as well as their consecutive memory address will need to be at 454. Okay. And again, you can find that information on the hand assembly lab register memory location document. All right, so those are the first 4, I should say 4 steps, counting this first step, step 3. So from here, I'm going to go ahead and I have a sample code pulled up that we're going to kind of start going through. And then we'll kind of move on to the next remaining steps. So first things first, I recommend as you're going through this lab is go ahead and start writing out your assembly instructions for what memory location you're going to use, as well as what registers you want to use. That way, once you have this all figured out, you can then start doing the hand assembly and deriving the instructions. Okay, so you can see here in my sample program, I'm going to continue with the consecutive memory address 454, as well as the register not used, being not using the D register in here. So you can see here I have move CL, and you'll notice that in the original program, I'll actually pull this side by side so you guys can see this a little bit. The original program, we have this move DX 120, but in here we have move CL 20. The reason why, again, is because these are 8-bit registers, so they can't hold 120, right? Because 0120 is actually a 16-bit value. So we have to modify whatever that value or immediate value we're putting into that register as an 8-bit value. So in this case, I just simply kept 20, all right? Now from here, the next thing we're gonna do is we're going to grab 1 byte of data at memory address 454. Now again, this is a valid instruction because of this reason. These brackets on either side indicate that we're actually handling a memory address. So in the architecture of the system we're using, it's each address is grabbing 1 byte of data, is the smallest amount of information we grab, right? I can't tell it, oh, grab 1 bit. I can only grab chunks of 1 byte at a time. So because of that, this address will do is grab at least 1 byte because we're only handling 1 byte, right? In the previous code, when you saw the move AX comma 200, what it was doing was it knew to grab the data at 200 and 201 and then store it into the AX. Because now we're handling AL, which is an 8-bit register, we don't need to worry about that. We can simply just tell it, hey, grab whatever byte is at that address. And you can notice I also butted up the data that I put the next bit of information for the BL right behind it. So before, in the original program, you can see there's a little gap between the data because, again, it's, or the addresses, because it's grabbing the data at 200 and 201 for AX, and then BX is grabbing the data at 202 and 203, okay? So it's grabbing that. Then from there, you can see we have this subtract instruction as before. We're doing our JGE. We do our add instruction, and the jump will go back to the JGE. And then we're going to store the data back to 454 and end the program. So here I'm going to go ahead and actually enter some data into my virtual machine. And you'll notice here that everything comes out. And also, we'll notice the instructions where they're jumping to, right? So when you first enter your program and you're doing steps 0 through 3, go ahead and don't worry about what addresses you put here right away, right? Or the space you're jumping. Just put something down, and then as you unassemble it, you can then figure out and calculate how many bytes are between those instructions that it needs to jump. So from here, you can notice that I'm jumping back. So it's 10B, right? So it's jumping back to this instruction. And again, JGE 111 is jumping back to the move and ends. And just to be thorough, I'm going to execute, and you can see the program terminates normally, and I'm going to check the data at 454 and 455. And you can see here, 1C is a positive value, and the original value, which was 5 stored there, is now done. So that's steps 0 through 3. Again, how we get started in this is you're going to, I recommend first writing out these instructions on a piece of paper or notepad and simply figuring out what's going on. I also want to make sure, note, this is also probably a good time, or this step is to modify your flow chart before you move on to other steps. So get this part done, make sure your code works, you've done the hand assembly and everything's working before you move on to the next continuing steps. All right, so next we'll talk about steps 4 and 5. So steps 4, what we're gonna do is after we've done the program, we've hand assembled, it's running, it's working, we're actually gonna modify our program to now display our name as well as a title to the program. Well, how we display titles is actually given an example lower down in the lab document down here. And so what you'll see here is we have seen move DX 200, move AH09, and interrupt 21. Interrupt 21 is actually a multi-service interrupt. So it has many purposes. So in the case of how it determines what it's doing is actually based off of what value we store into the AH register. So storing 09 into AH will simply tell the system we want to display a message on the screen, and that message is being stored at memory address 200. So that's why we store that 200 immediate value into the DX. So again, how that will kind of work is we call interrupt 21. First thing it does is it pulls up AH. It says, okay, what type of service am I running? Oh, I'm displaying a message to the screen. Well, then I'm going to grab the contents of AX and start printing a message onto the screen. And you can see here, we need to make sure we enter that message into our memory. So in this case, there's actually an easy way to enter strings without having to hand convert all the ASCII into hex. And that's simply doing the E200 space and then the quotation marks to indicate that it's ASCII. Now, the key thing we should always remember in this, when entering a string into memory is this right here. So that $sign actually is indication of what's called a null terminator. And this is an indication of end of the string. All right. So as it goes through, like I said, that process of interrupt 21, what's going to happen is it's going to start printing. And again, there's no point that we indicated towards the system how long our string is because it doesn't know. So it's going to simply just keep printing and printing and printing until it encounters a null terminator. And in this case, that's what we have here. Okay, and I'll actually show you an example of what happens when you don't have a null terminator. All right, so from here, the 0D and 0A is also important in the sense of displaying the string properly. This is just a carriage return and line feed, so it's going to reset that cursor to the next line. Okay, so let me go ahead and go back up to Lab 1 Part 2, and I'll go ahead and show you an example of just how to display the message onto this screen. Okay, so again, here's my instructions. Oops. Here, I'll go ahead and do this. I'll copy. And you'll see here I have my code now entered into memory address 100. And the other thing I'm going to show you here is I've entered my string into memory, right? So I did my E200, it has my message. Now, this is, when we worked through part 1, we told you to focus on what's the data inside when we're entering our program, as well as the data we're using for memory address 200. So now that we're dealing with string, what's useful is also this third column right here. So all of this data here was representing is ASCII characters. So we can see here that our actual ASCII characters was properly entered into the data into memory, right? So just keep that in mind. It's good to double check your string is entered properly, and most importantly is to double check that that null terminator is actually there. Okay, that's also going to be hex 24, by the way. All right, and now from here, I'm just going to simply run my program, and you can see I displayed my message screen, and my program terminated normally. Okay, now from here, what we're going to do is we're actually going to talk about why it's important that we put the null terminator. So I'm going to actually show you an example that will break your code. So what if you encounter this issue, you kind of can guess what the cause was, right? So I have my string, but I changed that null terminator now to be just an ASCII character 0. So you can actually see here there's an ASCII character 0 instead. Now if I do G equals 100, so it printed my string, but it kept printing all of these characters. So these weren't necessarily ASCII characters, but it just kept printing them because nothing indicated the end. And eventually the program stopped, or something caused it to stop printing, either it encountered a null terminator or something, and you just get all this garbage on the screen. So if you encounter this problem where you see a bunch of garbage appear on your screen, it's most likely because you forgot to put your null terminator at where you're printing, or you're printing from an improper location in memory. So what I mean by that is if this is not the correct immediate value, okay? So if my string isn't stored at 200, maybe I stored at a different address before that, like 180, and it starts trying to print, my string may not be until later, until a different area, and never encounters it. So just please keep that in mind. And so that's how we display titles to strings. So now we have to integrate this into our program. So how do we do that? Is actually, we're just going to take these 3 instructions and just simply plop them at the very beginning. Okay. And the other modification I'm going to make is we're going to make 460, because again, my consecutive memory address is everything after 454. So I'm going to go ahead and throw my string in at 460. Okay. Now, for those who are worried, you don't have to do the hand assembly for that part. Is actually we already provided to you for the most part. You might just have to modify some information, right? So if you look at this page here, again, you'll notice that we already kind of pretty much give you the instruction binary, right? The only difference is this data right here, which is stored in a little endian, right? We might just need to flop the data and change those 2 bytes, but you don't have to do the hand assembly for it. It's for the most part been already provided for you. All right, make sure I get to the right part again. There we go. All right. So so now we're going to add that message. So you can see here, here's my assembly. I'm going to go ahead and enter my program. Oh, excellent. And you can see here, I have my program. And again, it's still starting at memory address 100. So this is important. Make sure even though your title is the very beginning of your program, that means this first instructions should start there, right? And everything else should go ahead and have the correct data. And now what I'm going to do is I'm going to copy my data into my registers. Don't Don't forget to enter your string, very important. And again, double check that null terminator. So just to be safe, right? Always after you enter a string, just double check, like, is it properly entered, right? So I'm looking here, I have my string, I have my null terminator, I'm good. Nothing worse than trying to enter your data and all of a sudden your program crashes. There you go. So you can see here that my string printed, I'm going to dump the memory at 454 and 455. And you can see here 1C, that's my expected value, right? So excellent. All right, so that's step 4. So we're just simply adding a title to our program, okay? Now the last step for step 5 is we're going to modify the program to keep track of how many times we actually go inside the loop, and then we're going to display this amount, okay? So overall, this is not too difficult a step. This kind of just throws some people off as we're going through it, but the key is just understanding what instruction we can use to make this a little bit easier. All right, so I actually have my program here and I've added my counter as well as a little bit more additional information. So one thing I'm using here is called the increment instruction, okay, the INC. So this simply means that I'm going to add 1 to whatever's at this memory address, okay? So what I'm doing is I'm storing a secondary string, 30, 0D, 0A, in $, okay? So 30 in hex is simply the ASCII character 0, okay? So I'll kind of give you an example. Let me go ahead and all right. There we go. So we can see here that we have characters 0 through 9 in ASCII, right? And the hex value for character 0 is 30. Now, if you look at 1, the hex value is 31, 2 is 32, 3 is 33, 34, 35, 36, 37. So pretty much a pattern is going on here, right? If we want to display a character from 0 to 9, we're just simply going to start at hex 30 and add 1 to that, okay? So what we want to do for our program is just simply store the ASCII character, because now we can increment this to display the number of times we count. Now, as a warning, it's perfectly fine if we just have expectations of your loop going at least no greater than 9 times, okay? It'll simplify the logic a little bit and make things a little bit easier, but just keep that in mind. So if for some reason you choose really large values, you should be fine. So you might just need to increase this immediate value we use for the add for our logic, right? All right, so we're going to increment this ASCII character every time we go inside the loop, okay? So again, the program's pretty much the same. We have our title, we have our logic where we grab the data and then we subtract, we do our JGE, and now from here we increment. So, and then we add. So this is important, is the order we do these 2 instructions. So with an increment instruction, we're adding a positive value 1 to another positive value, which in our case might be 30 or 31 or 32, which this would cause the sign flag to actually flip. So if we're in our loop, right, our sign flag is negative. So it's means our value, or the last result of our subtraction was negative or our add. And so what'll happen is this increment will actually cause it to flip and become positive again. Well, what if we do our add and our add result is still negative? Well, if we put this increment instruction, I'll kind of show you what I'm talking about. So like this. So if we put our increment instruction, so we go through, let's walk through it. So we have a negative result from subtract. We check, we draw up through, we do our add and say our add isn't sufficient. So it's still negative. We go to our increment, our sign flag now flips to positive. Well, it jumps back up and says, oh, the sign flag is positive, drops down and ends the program. But AL is still negative. So how we prevent this from happening is we want to make sure we put this increment instruction before the add instruction, okay? So what'll happen is we go through, we subtract, we get a negative result, we drop through, we increment our counter, it flips that sign flag back to positive. We add, say our result's still negative, it'll flip the flag back to back to represent negative, and then it jumps and it says, oh, the value is still negative, and it drops back through. So again, if it's important to kind of confirm or double check your logic and ensure that you're covering all different corner cases, okay? Now, the last part we talked about was we have to display this count. So luckily, we're storing our data and we're incrementing it as a string. So it's very easy for us to display. We don't have to do any additional steps to convert it. So what we're going to do here is after we move AL, we're going to do move DX 456 because we want to now display this character, right? So 456 and then AH and then 21, right? So we're going to display it again and we're going to end our program. So I'm going to go ahead and I'm going to enter this program. Oops. All right, perfect. So you can see my program's entered. My jumps, let's double check. 112 is our JGE, 1011C is our move. So that's a good thing to double check because again, now we put this increment instruction in between our loop, right? So this is going to change the distance that things have to jump. So we have to make sure we double check that, and you'll have to adjust those two instructions as well. All right, good. Now let's go ahead and let's enter our data into memory. All right, and then finally, what I'm going to do is I'm going to run my program, right? Excellent. And you can see, so I print my title out, and you can see it actually went through my loop one time. So let's dump 454 and 455. And see, we got our 1C and 09. All right, excellent. So the last thing I want to discuss before I wrap up this video is I want to discuss the tracing chart aspect. So when we go through your program, you'll need to do a tracing chart. Don't trace into interrupt 21s. Just like we tell you don't trace in interrupt 20s, you're going to spend a long time going through your program, okay? And so, and especially for information we don't want you to worry about within the system and within a subroutine. So what we want you to do is we actually want to jump over this title. So that way, when you're actually tracing, you're only focusing on the logic of the program. So like right here, these instructions are really the ones we want you to focus on tracing, okay? So how do we jump through the program, or how do we go through the program and then start tracing? We're gonna utilize those breakpoints that we discussed in part 1, okay? So I'm gonna go ahead and put G equals 100 and 107. So again, 107 is important because that's the first instruction after interrupt 21. So I wanna run and execute this program and then stop right there. Boom. Now from here, I can trace through my program, right? Boom. And once I see interrupt 21, stop. I don't want to go any farther, okay? So that's one of the key factors when you start focusing on doing your traces is please double check and make sure you don't start tracing from the very beginning, okay? Go ahead and make sure you're tracing through the logic of the program, and to ensure that you can just simply grab create a breakpoint at the first instruction after the first interrupt 21, which should be at 107, okay? So, and then the final thing I'm gonna leave you guys with is that the demo requirements, we have to have 2 flowcharts. We have to have, so we're gonna make just edits to the part 1 flowcharts. Actually here, I'll show you guys the demo requirement videos. So I'm sure that will be a much easier table to look at. All right, so the part 2 requirements. So you'll need to have your hand assembly chart filled out with your new modified program. Just go ahead and add the instructions as we're going. You'll need 2 flowcharts. The first one with your hand assembly program, so the modification without the JGE. And the second one, go ahead and add a subroutine or box in the beginning, simply showing that as the title, and then add the additional instructions or steps regarding the counter and displaying of it, right? You'll need 2 runs, again, with 1 going into the loop. And you can see I just traced through my entire program. It's very quick if you just use your breakpoint and then go through the logic of your program. You'll need to do, you'll need to demonstrate this running. So I'm first thing when we demonstrate this in the final program, I'm gonna say, okay, have the final program and all of the data entered into memory, and then you're going to type G equals 100 and then display that it's working properly. Please choose values of data that are at least go through the loop more than once. All right. And then you're going to continue on the C program that you've done in in part 1, which this time all we're expecting is the same kind of C program. You're going to modify it to include a title and a counter into the steps. Okay. So that's it for the lab 1. Part 2, helpful hints or kind of description to kind of get you guys going through and doing everything. I highly recommend watch this video, watch it in different steps, go through the process. It's not overly difficult once you start getting into it, okay? But don't procrastinate. Try to put a little bit of time into it each day, and it will actually be fairly quickly processed. All right, so if you have any other questions, please email your lab instructor or contact them, and they'll be happy to help you.